Hi, Stu Schwartz from MasterMathMentor.com. This is video AB27. The topic is definite integrals, and it covers the AB manual pages 164 through 166. This course started off with defining the concept, the slope of the tangent line to a function. We developed a term for that concept, the derivative. We will do the same for areas under the curve. We define the term for the area between the function f of x, the x-axis, and the lines x is equal to a and x is equal to b as the definite integral. We write this using the notation you see on the screen and read it as the definite integral between x is equal to a and x is equal to b of f of x dx, or the definite integral of f of x dx between x is equal to a and x is equal to b. We call f of x the integrand. It is the function we are integrating. And we call a and b the limits of integration, where a is the lower limit and b is the upper limit. This expression might not make sense, but as usual, there is a reason for it. It refers to Riemann sum rectangles, which we will discuss in detail in chapter 29. In the figure, we examine one Riemann sum rectangle. Its height is f of x, and its base, or width, is delta x. We know that delta x and dx are the same thing. So f of x times d of x times dx is just another way of specifying the area of a rectangle. Note that we say that the area of the rectangle is approximately equal to f of x times dx because it is not an actual rectangle. As soon as it has a bit of a width, delta x, the height is different on the left-hand side and on the right-hand side. It is more trapezoidal shaped than it is a rectangle. But when delta x is very, very small, this will be very close to the area of a rectangle. The definite integral represents the limit of the sum of these areas. The integral sign looks like a flattened S for sum, as the number of rectangles approaches infinity, which is saying that dx approaches 0. So the definite integral from a to b of f of x dx means the sum of the areas of infinitely thin rectangles, starting at a, giving at b, ending at b, giving the figure that you see on the screen. Note that the definite integral sign is the same as the indefinite integral sign, except definite integrals have limits of integration. This is intentional, as we will find a connection to the process of taking an area under a curve and taking antiderivatives, as we just did. We will discuss this in chapter 30, the fundamental theorem of calculus. Whenever you see a definite integral, the integral from a to b of f of x dx, I want you to always think area under the curve f of x. However, we do have to be careful. We know that areas are always positive, but definite integrals can be both positive and negative. This is summed up by the table in yellow. The sign of our definite integral will be based on two factors: the relationship between a and b, the limits of integration, and whether the function f is above the axis or below the axis. There are four possibilities. Let's examine each. First, let's suppose that a is less than b. That means we are going from left to right, and that means that dx is greater than 0, which is positive. Also, f of x is greater than 0, meaning that f is above the axis. So when we look at f of x dx, that is a positive times a positive, which is a positive. And therefore, the integral from a to b of f of x dx will be greater than 0. Let us suppose that a is less than b, meaning that we're integrating left to right. But f of x is less than 0, meaning that f is below the axis. Therefore, our f is negative, our dx is positive, and therefore our result is negative. So in this case, the integral from a to b of f of x dx is less than 0. Let us suppose now that a is greater than b, meaning that we're integrating right to left, and dx is now less than 0. So if f of x is above the axis, meaning it's positive, then the integral from a to b of f of x dx will be a positive times a negative, which is negative. So our integral from a to b of f of x dx under that situation will be less than 0. And finally, let's suppose that a is greater than b, meaning that we're integrating right to left, and dx is less than 0, and f of x is less than 0, meaning that f is below the axis. So the integral from a to b of f of x dx will be a negative times negative, which is a positive, and therefore the integral from a to b of f of x dx will be greater than 0. There are 5 very simple rules for definite integrals that make total sense when you think about it in terms of an area. Number 1 states that the integral from a to a of f of x dx is equal to 0. If we start at a and end at a, then all we have is a vertical line, which has no area. So any integral from any constant to itself is always 0. Number 2 states that the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. When we integrate from b to a, we get some value, a number. This will be the negative of the value if you start at a and end at b. So you may switch the limits of integration as long as you negate the integral. That is true for any integration problem. Number 3 states that the integral from a to b of k times f of x is k times the integral from a to b of f of x dx. So, like with indefinite integrals, you can move a constant in and out of a definite integral. Number 4 reads, the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. This states that the integral of a sum is the sum of the integrals. That is true whether we're working with indefinite integrals or definite integrals. The 5th rule says that the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. This states that if you add the area from a to b to the area from b to c, you get the area from a to c. It makes no difference whether a, b, and c are positive or negative numbers. This statement still always holds. In number 1, you are given a piecewise function called f of x, defined on the interval -4 to 10. The function is defined as a series of straight lines along with a semicircle. There are a number of definite integrals you are to calculate, and since we are working with lines and a semicircle, these turn out to be geometry problems. It should be noted that even though the function is called f of x, all of these integrals are defined as in terms of f of t dt. It makes no difference what that variable is. We could have said f of k dk or f of w dw. The important thing is the name of the function, which is f. Whether we're talking about the t-axis or the x-axis, we are still talking about an area under a curve. A asks for the integral from 4 to 4 of f of t dt. Any definite integral whose limits of integration are the same, the answer is always 0. B asks for the integral from 0 to 1 of f of t dt. This is simply the area under the curve from 0 to 1. And since the curve is a horizontal line between 0 and 1, this is simply the area of a rectangle, 1 by 2, and therefore the answer is 2. C asks for the integral from 1 to 3 of f of t dt, and that is a right triangle with base 2 and height 2, which is 1/2 base times height, which is 2. D asks for the integral from 0 to 3 of f of t dt. And since we've already calculated the integral from 0 to 1, and then from 1 to 3, our answer is simply 2 plus 2, or 4. E asks for the integral from 3 to 6 of f of t dt. Our dt is positive as we are going from 3 to 6. But our function is negative as it is below the x-axis. So our integral will be negative. This is simply a triangle with base 3 and height 1, so the answer is negative 1.5. F asks for the integral from 6 to 3 of f of t dt. Since part E was the integral from 3 to 6, then the integral from 6 to 3 will be negative of what the answer to E was, or positive 1.5. G asks for the integral from 0 to 6 of f of t dt. We've calculated the integral from 0 to 3 in part D. We've calculated the integral from 3 to 6 in part E, and therefore the answer is 4 minus 1.5, or 2.5. H asks for the integral from 6 to 10 of f of t dt. This is a semicircle with radius 2, and therefore the area is 2 pi. I asks for the integral from 10 to 6 of f of t dt. Since part H had the integral from 6 to 10, then the integral from 10 to 6 is negative 2 pi. And J has the integral from 0 to 10 of f of t dt. We've calculated the integral from 0 to 6 in part G and 6 to 10 in part H, and therefore your answer is simply 2.5 plus 2 pi. K reads the integral from 10 to 0 of f of t dt. Since we previously did the integral from 0 to 10 of f of t dt and got 2.5 plus 2 pi, we will simply negate that, and this will be the answer, negative 2.5 minus 2 pi. Number 11 reads the integral from negative 1 to 0 of f of t dt. This is a trapezoid, and the area is 3. As we go left to right, the dt is positive and the function is positive. Number 5 reads the integral from negative 3 to 0 of f of t dt. This involves some work. We first look at the integral from negative 3 to negative 2 and realize that that's a right triangle with base 1 and height 6, so its area is 3. From negative 2 to negative 1, we can think of that as a trapezoid or a right triangle sitting on top of a rectangle. The rectangle's base is 1, its height is 4, and therefore its area is 4, and the right triangle has an area of 1. So we have 3 plus 5 plus 3, and the total area is 11. So n reads the integral from 0 to negative 3 of f of t dt. Since negative 3 to 0 is 11, 0 to negative 3 will be negative 11. O reads the integral from negative 4 to negative 3 of f of t dt. As we go left to right, the dt is positive, but the function is negative. So we have a small right triangle with base 1 and height 1, and the area is negative 1/2. So the integral in P from negative 4 to 0 of f of t dt is simply the integral from negative 4 to negative 3, which was negative 1/2, plus the integral from negative 3 to 0, which is 11, and our total area is 10.5. Q reads the integral from negative 4 to 10 of f of t dt. We can break this up in a bunch of ways, but part P did the integral from negative 4 to 0, and on the previous page we also did 0 to 10. So this turns out to be 10.5 plus 2.5 plus 2 pi, and the answer is 13 plus 2 pi. R asks for the absolute value of the integral from negative 4 to 10 of f of t dt. We just did the integral from negative 4 to 10 of f of t dt, which is 13 plus 2 pi, which is a positive number, so the absolute value of that is still 13 plus 2 pi. S is slightly different. It asks for the integral from negative 4 to 10 of the absolute value of f of t dt. To absolute value of function means that it will always be positive. So the function is mostly positive except between negative 4 and negative 3 and between 3 and 6. So the absolute value of the expression will take those two parts and bring them above the x-axis. And therefore our total area will now be 17 plus 2 pi. To do t, the integral from 1 to negative 1 of negative 2 f of t dt. This can get tricky, but we can make it easy by bringing the negative 2 to the outside, and also realizing that if we switch the limits of integration and go from negative 1 to 1, we can make the expression positive 2, integral from negative 1 to 1 of f of t dt. Since the integral from negative 1 to 0 is 3, and from 0 to 1 is 2, the integral from negative 1 to 1 is 5. Multiplying that by 2, we get 10. In number 2, you are given some information about functions f, g, and h. You're told that the integral from negative 2 to 5 of f of x dx equals 18. The integral from negative 2 to 5 of g of x dx equals 5. The integral from negative 2 to 5 of h of x dx equals negative 11. And also the integral from negative 2 to 8 of f of x dx is equal to 0. It is important to understand what these statements say and what they do not say. Remember that an integral represents an area under the curve. So when we're saying that the integral from negative 2 to 5 of f of x dx is equal to 18, and that is a positive number, it does not mean that the function is completely above the x-axis between negative 2 and 5. Indeed, it may dip below the x-axis for a good part of that interval. What it does say, though, is that there is more area above the x-axis than below the x-axis. The same is true for the g function. But for the h function, there is more area below the x-axis, from negative x equals negative 2 to x equal to 5, than above the x-axis. And in the last statement, the integral from negative 2 to 8 of f of x dx is equal to 0, it means that there is the same amount of area above the x-axis as below the x-axis between x is equal to negative 2 and x is equal to 8. You are given 6 definite integrals to calculate, given the definitions above and the rules established on the previous page. In A, you're asked to find the integral from negative 2 to 5 of f of x plus g of x dx. We can break this up into two integrals, the integral from negative 2 to 5 of f of x dx plus the integral from negative 2 to 5 of g of x dx. And since we have both of those values, 18 and 5, our answer is 23. On B, we're asked to find the integral from negative 2 to 5 of f of x minus g of x minus h of x dx. As we did in A, we can break this up into 3 integrals, and we have the values of each. So our answer is 18 minus 5 minus negative 11, and the answer is 24. In C, we're asked to find the integral from 5 to negative 2 of 4g of x dx. We can switch the limits to an expression that we know and write the integral from negative 2 to 5 as long as we negate the integrand. So this becomes negative 4, the integral from negative 2 to 5 of g of x dx. And since that integral turns out to be 5, our answer is negative 4 times 5, or negative 20. In D, we're asked to find the integral from negative 2 to 5 of g of x plus 2 d of x. We break this up into 2 integrals, the integral from negative 2 to 5 of g of x dx plus the integral from negative 2 to 5 of 2 dx. We know the integral from negative 2 to 5 of g of x dx is 5, as it's given. But the integral from negative 2 to 5 of 2 dx, you have to think about what this means. This represents the area under the curve, y equals 2, from negative 2 to 5, as shown in the picture. So this is simply a rectangle, okay, whose height is 2 and base is 7. And therefore our answer is 5 plus 14, or 19. E reads the integral from negative 2 to 5 of f of x minus 6 dx. So this becomes the integral from negative 2 to 5 of f of x dx minus the integral from negative 2 to 5 of 6 dx. We know the integral from negative 2 to 5 of f of x dx is 18. And the integral from negative 2 to 5 of 6 dx will be, like part D, a rectangle whose height is 6 and whose base is 7. So we have 18 minus 6 times 7, and the answer is negative 24. F reads the integral from negative 2 to 5 of 1/2 h of x plus 5 dx. So we can write this as 1/2 the integral from negative 2 to 5 of h of x dx plus the integral from negative 2 to 5 of 5 dx. So we have 1/2, that integral from negative 2 to 5 of the h function is negative 11. And again, realize that the integral from negative 2 to 5 is simply a rectangle with height 5 and base 7. So our answer is 1/2 times negative 11 plus 35, and the answer is 59 over 2. We have 6 more problems using the same information that we had on the last page. These problems, however, focus on horizontal translations, which will affect the limits. G asks for the integral from 0 to 7 of h of x minus 2 dx. To do this, you have to realize that h of x minus 2 shifts the h curve 2 units to the right. So the integral from 0 to 7 of h of x minus 2 dx is really the integral from negative 2 to 5 of h of x dx. Again, if we shift the h curve 2 units to the right, our limits now become 0 and 7. And we know that that answer is negative 11. H asks for the integral from negative 4 to 3 of g of x plus 2 dx. G of x plus 2 shifts the g curve 2 units to the left. So the integral from negative 4 to 3 of g of x plus 2 dx equals the integral from negative 2 to 5 of g of x dx. Again, if we start with the integral from negative 2 to 5 of the g function and shift it 2 units to the left, we get the integral from negative 4 to 3 of g of x plus 2 dx. And we know that answer is 5. I asks for the integral from 5 to 8 of f of x dx. We know that the integral from negative 2 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx is equal to the integral from negative 2 to 8 of f of x dx. So the integral from 5 to 8 of f of x dx is equal to the integral from negative 2 to 8 of f of x dx minus the integral from negative 2 to 5 of f of x dx. And we are given both of those values. 0 minus 18 equals negative 18. J asks for the integral from 8 to 5 of 1 minus f of x dx. We generally prefer integrals to have the lower limit on the bottom, so we will exchange the limits while making the expression negative. So this becomes the integral from 5 to 8 of f of x minus 1 dx, which is the integral from 5 to 8 of f of x dx minus the integral from 5 to 8 of 1 dx. We've already calculated the integral from 5 to 8, and we know that that's equal to negative 18. And the integral from 5 to 8 of 1 dx is the area under the curve y equals 1 from 5 to 8, which is simply a rectangle of area 3. So our answer is negative 18 minus 3, which is negative 21. In K, the integral from 1 to 8 of f of x minus 3 plus 3 dx, there are two shifts going on. First, realize that our f curve is shifted 3 units to the right, so this becomes the integral from negative 2 to 5 of f of x, and we then have the integral from 1 to 8 of 3 dx. We know that the f curve from negative 2 to 5 is 18, and we know that the integral from 1 to 8 of 3 dx is simply the area under y equals 3 from 1 to 7, which is a rectangle that is 3 by 7, and therefore our total answer is 39. L reads the integral from 2 to 9 of 2 f of x minus 4 minus 6 dx. In order to do this, we break it up into two integrals, and we took the 2 to the outside, and we realized that f of x minus 4 is really the same as the integral from negative 2 to 5 of f of x dx. So this becomes 2 integral from negative 2 to 5 of f of x dx minus the integral from 2 to 9 of 6 dx. We know that the integral from negative 2 to 5 of the f function is 18, so we have 2 times 18. And the integral from 2 to 9 of 6 dx is simply the area under y equals 6 from 2 to 9, which is a rectangle with height 6 and base 7. So we have 2 times 18 minus 6 times 7, and our answer is negative 6. When you think of taking a derivative of a function, two thoughts should go through your mind: a meaning and an algebraic procedure. The meaning is a formula for the slope of the tangent line to that function at any point. The procedure is the power rule, product, quotient, or any of the differentiation rules taught. The same is true when taking a definite integral. Right now, all we have is meaning. Eventually, though, we will have an algebraic procedure. But for now, when you see a definite integral, you must think area under a curve. In the following 4 problems, to find a definite integral, sketch the functions, which will be series of straight lines. If you don't know the shape, plot points in the intervals from negative 3 to 3, and then use basic geometry rules to calculate the definite integral. A reads the integral from negative 3 to 3 of x plus 2 dx. We know x plus 2 graphs a line with a y-intercept 2 and x-intercept negative 2. We see it on the screen, and therefore the definite integral will be the integral from negative 3 to negative 2 of the function, which will be negative 1/2, plus the area under the curve from 2 to 3, which is 25 over 2, and the final answer is 12. B is the integral from -3 to 3 of the absolute value of x plus 2. So this takes the previous curve and makes anything that was negative positive, creating a V shape. And therefore, our integral will now have the value of +1/2 plus 25 halves, or 13. C reads the integral from -3 of the absolute value of x plus 2 dx. The shape is on the screen, and again, you can get this by plotting points. Since this is symmetric, we can just calculate the area from 0 to 3 and double it. You can think of that as a trapezoid, or you could think of it as a right triangle sitting on top of a rectangle. If we think of it like that, the rectangle has area of 3 by 2, which is 6, and the right triangle has an area of 3, base 3, and height 3, which is 9 halves. So 2 times the quantity 6 plus 9 halves is 21. D is the integral from -3 to 3 of the absolute value of 2 minus the absolute value of x dx. Plotting points, we get the sawtooth shape that you see on the screen. Again, this curve is symmetric to the y-axis, so we can just calculate the integral from 0 to 3 and double it. This is two right triangles, one with a base of 2 and height of 2, and one with a base of 1 and height of 1. So our area will be 2 times the quantity 2 plus a half, and the total area is 5. If you would like to understand the equation, capital F of x equals the integral from a to x of f of t dt, and how it relates to the picture on the screen, you'll have to stay tuned for the next video that covers the accumulation function. Stay tuned.